Good evening, everyone. Today we will start with this atomic optical spectrometry. If you see, there are three words: atomic, optical, and spectrometry. We have all seen what spectrometry is. Then we have this optical. What is optical? We know it is associated with optics, right? So optics is basically visualization. Okay, so if you look into the optical spectrometry, it's similar to the visible spectroscopy. But now you would ask me, sir, we have already covered visible spectroscopy. Then again, why we want to go for this optical spectrometry, atomic optical spectrometry? The difference, what we will be studying, lies over here. The word atomic. Atomic optical spectrometry and normal visible spectroscopy, they are different in terms. In visible spectrometry, we are basically interested in the electronic transition. Okay, so the electrons within the molecules, they were being excited, and while they were coming back to the ground state, they were emitting the photons. Whereas, as the name atomic optical spectrometry suggests, in AOS, atomic optical spectrometry, we have atoms. Okay, now these atoms, they are being excited, and when they come down to the ground state, they emit light. So just हेलो, हाँ जी बोलिए. हाँ. नहीं नहीं नहीं, आप मुझे नहीं चाहिए. थैंक यू. Sorry. So when these excited atoms, they come down to the ground state, during this process they emit light. Okay, and herein, in atomic optical spectrometry, we analyze this visible light. Okay, so I hope everyone has understood what is the difference between normal visible spectroscopy and atomic optical spectroscopy. Okay, now before going into the details, I would give you, or I will tell you, the different methods or different analytical techniques which are based on atomic optical spectrometry. As the name suggests, that atomic optical spectrometry, it it is dealing with the excitation of the atoms, and when they are coming back to the ground state, they are emitting light. But we can uh, excite the atoms in different ways. Okay, so what happens over here is that if you look over here, there are three arrangements, and you can what you call, you can just compare them, compare these methods or analytical techniques with the methods what we have already discussed. The first one is atomic absorption spectroscopy or spectrometry, which in short we call AAS. atomic absorption spectroscopy or atomic absorption spectrometry. Okay. Now this is similar to the UV vis spectroscopy. Okay, UV vis spectroscopy. Now herein we have a light source. Usually the light source in this atomic absorption spectroscopy, we use hollow cathode lamp, HCl. Now we have this lamp over here, and then the light emitted from this hollow cathode lamp is incident onto the sample. But what is the sample over here? Sample can be any, it can be in the form of solid, or it can be in the form of liquid, but it is being atomized using the atomizer. Okay, it is being atomized and being using this atomizer, and they are sent to the excited level using this energy transfer method. In general, we have that energy transfer, we do it by what you call, by oxidizing the metals within a flame. Okay, so we have this flame atomizer. So atomizer which uses the flame, it is regarded as flame atomizer. So over here we will be having the sample which are burning or atomized within the flames. Okay, now you have the incident light, you have the transmitted light. Now then, just like any other spectroscopic technique, you have wavelength disperser. Okay, so that will decompose the light. Okay, and then you can use a monochromator also, if you are this interested in the just in this I0 or the wavelength of the light which you are getting it from the hollow cathode lamp. Then you just use a band pass filter, optical band pass filter, then you take it to the transmitter for readout. Okay, so if you are just interested in only one wavelength, lambda, say lambda HCl, then you can use a photodetector. Okay, now it can be used for qualitative purpose, where at a particular lambda we can prepare the standard curve for a particular metal ion. So over here we will be having the concentration and the absorption similar to what we have got in the Beers-Lambert's law. Okay, and from there we can read out read out the concentration of the unknown solution. Okay, the second one, if you see, we have atomic fluorescence spectrometry. Okay, atomic fluorescence spectrometry. Okay, so in this atomic fluorescence spectrometry, so it is similar to the, as the name suggests, it is similar to the fluorescence. Okay, so the light source and the detector, they will be 90° apart. Okay, so that is there, and here mercury lamp it is used. Right, so rest of the arrangement, you have the atomizer over here also, so you get the thing. Now, lastly, we have atomic emission spectrometry, AES. Okay, and over here, uh, it is corresponding to just like luminometry, what we discussed in our last class. Okay, so it is simple to it is similar to that one. So if you see, you have the sample on its own. There is no excitation source. There is no light source over here. In case of the atomic emission spectrometry, you will just have this atomizer. Here also you can use the flame atomizer. Okay, and then whatever the emitted light will be there from the samples, they are being emitted. Okay, so you can go for the wavelength dispersion, and from the wavelength dispersion, if you get the spectrum from each of these, from that information you can get the information about the what you call you can get the fingerprint of a particular compound, and from that fingerprint you can go for the qualitative analysis. Sorry, I have wrote qualitative over here. This is quantitative. Okay, right. So fingerprint region analysis, it will help us in the identification of the compound. Okay, and you can do it in any of this method. Okay, however, if you see this one, this light source, and over here you are exciting it with a particular wavelength, and then you are analyzing the spectrum. Here in the atomic fluorescence spectrometry, you are exciting the sample at a 90-degree, and then usually we have seen that in the fluorescence, so whatever the excitation wavelength is there, we use a monochromatic wave for the excitation. So here also we get a monochromatic signal, and from there the samples are being excited, and then you do the analysis just like whatever you have done in the fluorescence spectroscopy. Okay, and over here just like in luminometer, during the atomization process, whatever the light will be generated, that light is collected, and that is analyzed. In this one you must have seen during your class 12 experiments, you must have done the analysis of some of the metals. Okay, in the loop, in the Bunsen burner, uh, you are having a flame, and using a this platinum loop, you put some sample over here. Okay, and when you put that sample over here, it emitted some radiations. Okay, some colorful radiations, and that you are visually observing. This atomic emission spectrometry, it is basically that, but in a more sophisticated way, and here you are able to analyze the whole spectrum. So this is basically a qualitative method, and this is also a qualitative method, but with more sophistication and much more accuracy. Here you cannot find out at what wavelength you are getting the bands and all these things. You may have several bands. Okay, so one of the band may be very strong, whereas the other bands will be very low. So you will be able to just monitor the strong band. But over here in atomic emission spectrometry, you will be able to analyze those bands also, right? Now, there are some problems with this flame atomizer, and hence uh, this AES has been modified to have ICP AES. So this atomic emission spectrometry, it is regarded as AES, and if you are using a flame, then it is called FAES. Okay, flame atomic emission spectrometry. Okay. Another variant of the AES is the ICP AES, which is much more what you call it is uh, in FES you will get a low signal to noise ratio. Okay, that means the signal component will be lower. Okay, however, when you're using the ICP, this inductively coupled plasma, what it does is that it increases the signal to noise ratio. Okay, and because of this reason, most of the commercially available AES, they are basically dependent on they employ this ICP AES. However, if you do not have money to buy this ICP AES, and if you want to do some preliminary studies uh, in your lab, then you can develop this atomic uh, emission spectrometry. What you have to do, you just have to go back to your class 12 standard no, practical. You take this uh, you take a Bunsen burner, you take the platinum loop, and whatever the procedure you have followed, you follow that one, and then you use a homemade spectrometer over there. And there are many resources available currently in the internet, and you will find it's very easy to develop these spectrometers. Okay, you just in a dark room, you just take the readings over there. Okay, so you will be able to get the information. Okay, it's just like video recording, you can record the stuff. Okay, so when you do that, you will be able to able to develop this atomic emission spectrometry very easily in your lab. Okay, but you will be having a low signal to noise ratio. But anyway, uh, what you say, there is a saying that you get what you pay for. So if you are not having a large amount of money to get this ICP AES, you design your own AES. It may be a flame AES, but it can help you in the preliminary understanding of the process what you will be doing. Okay. So over here, do you have any question?
No, sir.
Anyone else? No? Okay. Yeah. Now we come into this thing. Configurations of the instruments for atomic absorption spectrometry. We have a lamp, and within this lamp we have a chopper. So what this chopper does, from here you will be getting a continuous beam of the light. Now this chopper, it breaks that light. Okay. So let me use another color pen. Oh, that is black. Okay. Initially, let's say you have a continuous beam, and then as we pass this chopper, we will be getting this chopped beam, and from here we get to the atomizer, and in a short period of time we'll be looking how the atomizer works. So as the name suggests, atomizer, that means the molecules will be converted into their respective atoms. Okay, and the process is called atomization. Okay, from here you will be getting the transmitted light, which is again will be the chopped signal, and then you have a wavelength selector, then you have a detector. This detector over here, it is a PMT, photomultiplier tube. We have already discussed about what photomultiplier tube does. Then we have the electronic components for amplifying the signals of the PMT, and then you can record the signal. Okay. So this is a single beam spectrometer. Okay. Now coming to the double beam spectrometer. In the double beam spectrometer, what happens, just like in the double beam UV visible spectroscopy, you have the signal, the from the source you are having the radiation source from here. It is being chopped. It is coming to a beam splitter. Now a part of the beam splitter, it is sending some of the signals to the atomizer. Okay. Then a part of the beam, it is being reflected. It is the reference beam. Then there is a beam recombiner that is getting combined. Now this beam splitter, what it does, it sends a signal at a fraction of time to the atomizer and another fraction of time to the this concave lens. Okay. Now it is being controlled by this electronics. Okay. Now when this recombiner, it is combining the beam and that beam is getting into the detector, these electronic components, this amplifier circuit which we have shown over here, which has been shown over here, it knows which one is from the reference, okay, and which one is from the sample. Accordingly, it stores the data in the data storage device. Okay, and from there you get the reading. Okay, so what happens? I'm just again repeating this. You have the lamp. From the lamp, continuous source of radiations are being generated. When it is coming out, it comes in contact with a chopper, which chops the signal, and it becomes a discontinuous radiation. Now this discontinuous radiation falls onto a beam splitter. So at one instance, this beam splitter, it sends a part of the beam to the atomizer, and in the next instance it sends the beam to the reference beam, and this beam splitter, it is being controlled by the electronic circuit whatever you have in the device. Okay, so in the meantime, what happens, the beam, it passes through the atomizer, you get the sample beam, and then you have the reference beam which comes to the this position where we have the beam recombiner. It combines the beam from the reference beam and the sample beam, but please remember that the electronic component, it has the information at what time it will be receiving the beam from the sample and from the reference this thing. Okay, then those beams, they fall onto the wavelength selector, they are being amplified, and after the amplification process, you have the electronics components which will read out, and it has all the information which is from the sample beam and which one is from the reference beam, and it will record that, and finally you will get the output. Okay. Now coming to the radiation sources.
Sir, excuse me, sir.
Yeah.
Sir, I'm having a bit of confusion in that atomizer part. Like, how does it actually work?
Yeah, I will come to that. I will come to that. Don't worry.
Okay, sir. Thank you, sir.
I just gave you the basic information how the instrument works. Okay. Now we will be getting into that. Slowly we will be looking into what are the what are the lamps we are having, and what are how this atomizer works, because the functioning of this atomizer is one of the great or one of the important things in this atomic optical spectroscopy. Okay, it's all about this atomizer basically. Okay, so quality of the atomizer will define what would be your signal to noise ratio in your final output. Okay, so we'll definitely discuss that. So coming to this radiation sources, so we will be basically talking about initially this atomic absorption spectroscopy. Okay, because it is most commonly used and in biological analysis, especially your if you are in environmental biotechnology. Even this is it is being used for what do you call this measurement of sodium, potassium, and other metal ions within the blood. So now from the blood we separate the serum, and from serum within the serum these metal ions will be there, and then we analyze those ions, those metallic ions within the serum, and we find out what is the concentration of that those ions within the blood or in a sample of water, whatever you say. So if you are an environmental scientist, you may be interested in a pond, um, in a pond. Suppose this is the pond. What is the quality of this one? What is the quality of the water over here? So you may be interested in understanding if there are any mercury within the within the within this water, whether there are sodium ions. Okay, so we are interested in this. So it's basically whatever you say, whether it is biomedical, whether it is environmental, whatever you talk about, you first have to understand what you are to analyze. If you say, I want to analyze sodium, I want to analyze potassium, and I want to know whether these metal ions are present within the these systems, then you have to choose which kind of analysis you want to do. Okay, so whether it is environmental, whether it is biomedical, doesn't matter. Your primary concern should be what you want to do with your sample, what analysis you want to do. Okay, so based on the what sample you want to analyze within a given sample, then you choose an analytical method. So understanding the mechanism of the uh, this analytical instrumentation and analytical techniques is of utmost importance. Once you have understood what you want to do, then you can make a judicious or conscious effort to understand, conscious effort to decide which type of analysis you do. Unfortunately, you will find many a days most of the researchers what they do is the other way. They prepare a sample and they say, I will do this, I will do that, I will do that. So they're just blindly putting their legs into different analytical techniques. But what I suggest is that you understand what you want to analyze. You may not be needing AAS or AES. Okay, so why you want to go for those, right? So anyway, so radiation sources, the different radiation sources, um, we will be talking about this AAS, atomic absorption spectroscopy. Okay, so over here we have hollow cathode lamp. So it is a cold cathode lamp. Okay, so and it is used in LS AAS. Then we have um, this electrodeless discharge lamp. It is also in LS. It is used in LSAS, and then we have deuterium hydrochloride, uh, which generates light sources in the range of at what do you call deuterium hydro this hollow cathode lamp. So it can generate wavelengths at 190 and 320 nanometer. It is also used in LSAS and continuum sources. This is used in continuous AAS. So xenon arc lamp. Uh, it generates radiations in the range of 190 nanometer to 900 nanometer. Now if you see, um, and this is a continuous spectrum. Okay, so xenon arc lamp, if you remember, we have talked about this xenon arc lamp in one of the spectroscopic methods previously, and if you see, it covers whole of the UV visible region. So when you are going for this xenon arc lamp, you can go for the measurement of the spectrum. Okay, and this LS means these lamps, they will generate a specific wavelength, um, and basically you can say you are getting monochromatic light from here. Okay, you are getting monochromatic light from here. Okay, however, so these continuum sources, in these continuum sources, what you have is that you can get this whole spectrum, and from here you can do the this quantitative measurement in a quantitative measurement of a metal in a particular ion. So among these three, this usually these hollow cathode lamps, these are commonly used in the commercial AAS. These are used in the commercial AAS, and we will just be discussing about this AAS or the hollow cathode lamps over here. Okay. Now this is the diagram of a schematic diagram of the hollow cathode lamp. So if you see, we have a glass enclosure. Okay, now this, within this glass enclosure we have a buffer gas, which may be neon or argon gas. In general, in most of the manufacturers, they prefer to develop this hollow cathode lamp using neon. Okay, so I'll be during my discussion, I will be talking about neon. Okay, I will be giving the mechanism how the radiations are being generated using the neon. Okay, neon gas. Now over here you have the glass enclosure, and we have seen that glass enclosure, they are only uh, what you call, they are optically transparent, but they are optically transparent in the visible region, and they are not, they are UV blockers. Okay, however, if you want to do some analysis using other range, then you may be interested in the UV region also. So usually what happens, for each and everything you cannot change the casing. So usually the glass enclosure is used. However, at the tip, this area from where the radiation will be generated, or the radiations will be coming out of the cathode lamp, it is made up of quartz. Okay, it is made up of quartz. Okay, now we have two electrodes, one is anode and one is cathode. Okay, the anode, it is made up of tungsten. Okay, and the cathode over here is made up of different metals. When I say that it is made up of different metals, I mean to say it may be made up of sodium, it may be made up of potassium. Okay. Now, how will you decide which metal cathode you will be taking? Suppose you want to find out the concentration of the sodium, then you have to take this sodium cathode lamp. If you want to measure potassium, then you have to take potassium cathode lamp. Okay. Now, between this tungsten and this anode and the cathode, a voltage of 500 to 1000 volt is applied. In general, it is what do you call around 500 volts. Sorry, it is usually kept in lower voltage range, but you may have a higher range also, and in some cases low power systems it may be near to 300 volts also. Some manufacturers, they have reported that the voltage source is around 300 volts. Okay, so usually it varies in between 500 to 1000 volt. Now what happens, as soon as you put on the voltage source over here, what happens between the anode and cathode, there is a very high voltage discharge, and due to this discharge, the neon gas which is present, it breaks down into Ne plus plus electron minus. Now this electron, it moves towards the tungsten anode, whereas this neon charged neon gas, it goes and it strikes the cathode. Now when it strikes the cathode, during this process, what it does, it dislodges atoms from here. Suppose this is sodium, it will dislodge the sodium metal from here. Okay, now likewise you will be having a lot of sodium ions which will be generated. Okay, now this process of striking of the neon plus ion and dislodging the sodium atoms, this process is called sputtering. Now when the sodium is being dislodged, they are at a high energy state. Say I put it as this dark here. Now they come out, and while they come out, they are at an unstable stage. They slowly start losing their energy, and during this process they come to the low energy state. Now see how I have represented a hollow circle. Okay, now when it is coming from high energy state to low energy state, it is emitting radiations. Now this radiation, it is a characteristic radiation, and in the case of sodium cathode, the radiation is emitted at 589 nanometer. Okay, so this radiation, it moves out of this quartz window. Okay, now what is the advantage of this radiation? The advantage of this radiation is that every time when you put on this lamp, you will be getting 589 nanometer radiation out from this lamp. Okay, so this is the main advantage of this thing. Another advantage, you will not need a monochromator. Okay, now another question it might arise, sir, why we have chosen only this thing, and you said if I have to analyze sodium, we have to use sodium cathode. Okay, The thing is that we have said that sodium ion, when it is in the excited state, it is having higher energy, and when it is losing the energy, it is emitting the radiation in a particular wavelength. Now, if I have to excite these sodium ions or sodium metals, then if I excite at this 589 nanometer, then only it will be excited. Okay, then only this sodium ion, sodium metal will be excited. Okay, and when I say sodium metal, I am talking about the sodium metal in the atomic level. If you remember over here what I said, it is removing the atoms from here. Okay, so when the atoms are removed, they are at a high energy state. These atoms are going into the low energy state, and they are giving a lambda max, say, or lambda sodium maybe. Lambda sodium. Okay. Now, if I have to excite another atom, I have to use this lambda Na to excite this sodium atom. This is the property of all of the metals. Okay. So if you excite them, and then if you uh, do the, what do you call, if you find out the spectrum, you will find a very strong peak at a particular region, and there may be other peaks, but that will be that will be having very small values. Okay, so this is why we use the hollow cathode lamp. This hollow cathode lamp, it gives us an opportunity to generate monochromatic light without using a monochromator. Okay, and if you use the optics also, if you use a monochromator, there will be optics and all this thing. There will be some bandwidth, optical bandwidth. Okay, so it may not be exactly 589. Herein you are getting the exact wavelength where you can strike the atom, with which you can strike the atom, and you can send the atom to the excited level. Okay. So this is a pictograph of a hollow cathode lamp. So if you see, this is the cathode, this is the anode. If you see over here, it is appearing as a lamp. It is appearing as a wire over here, and then you have this cathode. In between, you are having this Ne plus ion, which are being excited. The metals are getting out. These metals are getting out at the excited state, and it emits radiation, and it goes to the low energy state. Okay, so uh, I hope up to now you have understood what I meant to say. The next is over here, the conduction at a lower voltage uh, with more current than a cold cathode lamp that does not have a hollow cathode. Okay. So over here, the conduction, it happens at a lower voltage, and when you use this hollow cathode, you get more current, because these sodium ions, they some of them, they may be going up, they may be striking that, and they are dislodging other metal ions also, and also you are getting a larger area. So because of that, you are getting this more current. Okay, so more of mm, this what you call charged neon gas, they are going and striking the uh, cathode. If it would have been just a wire, it would have got a very small area, and due to that reason, the effectivity of the sputtering would not have been quite high. Okay. Now sputtering, the ionized buffer gas ions are accelerated towards the cathode that results in the sputtering of the atoms from the cathode. Okay. Then line source LS, AAS, and it is the characteristic radiation. Okay, characteristic radiation, and also we sometimes call it K-shell radiation. Okay, so we all know that we have an atom, and then this you have this electronic orbitals are there. Which one is the K-shell over here? Which one is the K-shell? Anyone? Hello.
Yes, sir. The closest orbit will be the
Yeah.
case.
So this is the K-shell. So the electrons from here, what happens? When these charged ions they come and they hit it, these and energize the sodium metal. These electrons they go to a higher this orbital levels, and when they come back to this region, to this cation, it gives a characteristic radiation at a particular wavelength. Okay, so that is called characteristic radiation, and every time you do it, every time you will be getting the same you will be getting the radiation at the same wavelength. Okay. Now hollow cathode lamps for an atomic absorption spectrometer. Now, if you see, as I said, if you want to go for sodium analysis, you will be needing a particular hollow cathode lamp. If you want to analyze potassium, you need to get potassium this thing. If you need to analyze any other metal ions, then you will be say manganese, then you will be needing another hollow cathode lamp. So in a typical atomic absorption spectrometer, you will be having a series of cathode lamps. Can you see? You are having same 1, 2, 3, 4, and more than that. Beneath that also there are something. So at least you will be having 7 to 8 cathode lamps within a specific spectrometer. Because as I said, these are needed to analyze. The more the number of the hollow cathode lamp you will use, the more amount of elements you will be able to analyze using the atomic absorption spectrometer. Okay. So then there is this atomizers. I feel we are just left with 2 to 3 minutes, so we will stop over there, and it will take a lot of time to discuss about this. Till now, if you have any question, anyone? So line source AS, we use hollow cathode lamp, electrodeless discharge lamp, deuterium halo cathode lamp. Okay, and for continuous source, we have this xenon arc lamp. Okay, these are basically used mainly for this quantitative analysis of the ions. You can do qualitative analysis, but that will be quite restricted because you will not get the full spectrum basically. Okay. Anything else you want to ask? No? So I will stop here.